start with a problem on how to use principle of conservation of angular momentum. So the physical situation of the problem is like this. I have a rod of length like this, and then it is rotating with the angular velocity omega naught, and then two small spheres of m each are attached gently to the two ends of the rod. This one m gets attached to here, two small spheres of mass m each are attached gently to the ends of the rod. What is the final angular frequency of the system? To find the omega of the system. Right. Now there are no external torques. So first thing we notice that no external torques. So principle of conservation of angular momentum applies. So what is happening is, as initially the rod is rotating about an axis with a particular angular velocity, therefore it will have certain amount of angular momentum. Now without disturbing the system, two masses m each are attached very gently to the rod at each end, one at each end. Therefore, since no external torques are there, therefore the angular momentum of the final system should be same as the angular momentum of the initial system. That's the idea. Angular momentum of the initial system is equal to omega I, moment of inertia initial times omega I. This is equal to ml squared by 12 omega naught. Now L final is equal to IF omega F. This is equal to, now IF alone I will write here. One is ml squared by 12 plus mass of little m is attached at each end, therefore this will have two masses, so each will have a moment of inertia. This whole thing will act with omega f. If we equate these two, we will get omega f is equal to ml squared by 12 divided by ml squared by 12 plus 2ml squared omega naught. Now we notice that the angular velocity of the final system is smaller than the angular velocity of the initial system. That is obvious because more mass has been added, therefore the moment of inertia is higher. Okay, I have the problem is like this. This is I have L. The problem is A. Like this is length is L. Then we have A. Here B. Length is. Then we have here this length is 4L. This length is 4L. This length is 2L. And then this length is 2L. This is three rods are joined. Three light rods. First I will take the rods to be right. Joined, case 1. Three light rods. First I will take the rods to be right. Case 1. the connecting rod is light. Let M be the mass per unit length of AB as well as CD. Right. Now, there is a force F, it will act at a particular point. This is at a distance x from here. This is from the center. So this length would be L minus x. Now, taking moments about P, moment of AB, we will calculate taking moments about P. Where is P? This is the point P. So I will have this mass AB M into L, that into X. Okay, that must be equal to, this is 4m times mass per unit length. Why m into L? This is the mass per unit length is m, therefore m into L. Then that is the mass, that times x, this distance. Similarly, in the due to this rod CD, it is 4m into L, 4Lm into the distance. This distance would be 2L minus x. So this implies x is equal to 8L by 5 is equal to 1.6L. The connecting rod has the same mass per unit length. The connecting rod has the same mass per unit length. Okay, then what will happen? From the top portion it will be the same, and from the top portion means from the portion AB, the moment due to AB will be the same, moment due to CD will also be the same. However, there is going to be a moment due to this portion, the middle portion, right? So therefore, into 2Lm into L minus x plus 4Lm into 2L minus x. So x is equal to 10L by 7. Principle of conservation of linear momentum and principle of conservation of orbital angular momentum. I will explain the problem. I have a rod, a uniform rod is on a table, okay, and masses m and 2m strike. There is a mass which comes and there is a mass 2m which strikes here, the rod, and there is a mass m which strikes here. As indicated in the bar below. Now the velocity of this mass is v. The velocity of this mass is 2v. Right? C is the center of the mass. And this distance is 3a. And this distance is a. This distance is a. Okay. 1. Determine to determine VC, velocity of the center of mass. That is first part. Okay. Right. Now we can make use of principle of conservation of linear momentum. Principle of conservation of linear momentum. What does it say? Principle of conservation. Initially the rod is at rest, therefore momentum of this rod is 8m times 0 plus the 2m strikes with a velocity v, but it is in the opposite direction. These two directions are opposite. This direction is minus v plus this mass m, it strikes with a velocity 2v. This is what is going to be the momentum of the initial momentum. This is equal to 0. What is the final momentum? Final momentum is equal to final momentum. There's one thing which I have not stated in the problem is the bar is that these masses 2m and m, they stick to the bar. The 2m and m, they stick to the bar. After striking. Therefore, now the total mass of the system is 8m plus 2m plus m. The whole thing will have one velocity, that is the center of velocity Vc. So you equate 1 and 2. This implies velocity of center of mass is equal to 0. Okay. So system will have, so since there is no translational motion, this implies no translational motion. So it will have only rotational motion. To calculate the angular velocity of the center of mass, right? So we have seen there is no translational motion, there will be only rotational motion, on no external torques are acting, therefore orbital angular momentum is conserved. Therefore, what is Li? Li is equal to 2m, that is the mass times velocity times a, plus little m times 2v times 2a is equal to equal to, what will be this value? This value would be 2 plus 4, 6 mVA is the initial angular momentum. So final angular momentum. Now after the masses get stuck to the rod is going to rotate with a omega. Therefore orbital angular momentum is whatever is the moment of inertia times omega. Now for this moment of inertia, the mass 2m will contribute, mass m will contribute, and also the rod will contribute because the entire thing will rotate. So first 2m into a squared. This is the moment of inertia. This is the moment of inertia of the mass 2m plus the moment of inertia of the mass little m cross 2a whole squared. Okay, 2m into a squared, m times 2. I am calculating all this with respect to the center of mass plus 8m into plus 8m into 6a squared by 12. 6a squared by 12. This is the moment of inertia of the rod about the central axis. Whole thing times omega. So this will give you 30 m a squared omega. So equate this to 30 m a squared omega is equal to 6 mVA. So m and m will cancel, a will get cancelled. I will have omega is equal to 5 by V divided by 5A. Now, what more can be calculated with respect to this problem? Now there is no translational motion. It is not moving parallel to any axis for that matter, but it is only rotating, and it has got an angular velocity omega which I have calculated. Therefore, the whole system, after the masses get stuck to the rod, it will have a rotational kinetic energy that can be calculated. So third thing is kinetic energy due to rotation. What is the expression? Even if you don't remember, if you remember linear motion, you can try to write down. And in linear motion, the expression for kinetic energy is half mv squared. Here, half, the role of mass is taken over by moment of inertia and then angular velocity squared. That is, so this is equal to half into, we have calculated what is the moment of inertia in this case earlier, that we have calculated 30 ma squared. Therefore 30 ma squared times omega squared, v by 5a the whole squared, that will give you 3 by 5 m v squared. Okay, so this is a good problem which requires the principle of linear momentum. It requires the conservation of linear momentum and also the conservation of angular momentum. Now we will do a problem which involves various concepts like slipping, etc. Okay. So this is a problem involving slipping. So when an object moves on rolls on the other object, it can simply slip. That means there is no rotational motion for it, and involving frictional force, etc. So I have a rod AB. There is a mass M. Okay, it is a distance of L units. MB. So M is a bead which can slide along the rod. Okay, this M is a bead which can slide along the rod without falling. Initially it is a distance L, as indicated here. It is distance, this is the initial distance, little capital L, sorry. The rod rotates about A with a constant angular acceleration. So it rotates, okay, with a constant angular acceleration alpha. Right. Now, yeah, the rod rotates. This is given. About A with a constant angular acceleration. The symbol for angular acceleration is generally alpha, which you must be knowing, which is constant. Mu is the coefficient of friction. Mu, the coefficient of friction. Mu is the coefficient of friction between the rod and the bead. Okay. So we can neglect gravity, then find the time after which. No, what is happening? There is a rod on which this mass is there. This is a bead. The rod is rotating about A with a constant angular velocity. So as it rotates, the bead can move along the rod. It can slide along the rod. There is a friction between the bead and the rod. So at some point of time, the mass has to slip. We have to find the condition for that, condition for slipping. Now, first thing we should note, alpha is given to be a constant. Alpha is constant. Therefore, the angular velocity is not constant. It has to depend on, therefore, the angular velocity has to be alpha times t. The reason is, if I take dw by dt, which is, I'll get my alpha. So first thing we should realize in this problem, that angular velocity is not constant. It depends, it linearly varies with respect to time. Right. So linear acceleration of the bead first. Linear acceleration of the bead. This is A. This is going to be. How is linear acceleration defined? Linear acceleration is the length times alpha. This is the definition. Then reaction force on the bead due to the rod. the reaction force on the bead due to the rod. Is equal, this I will call it a N. This must be same as M into A. This is M into L into alpha. Now, and we have taken this angular velocity to be alpha times T. Now there is a centripetal force on the bead. Centripetal force on the bead is equal to M to, what is the expression for centripetal force? Or theta dot squared, where theta dot is, if you had forgotten, d theta by dt, that is nothing but the omega, right? Therefore this term is equal to centripetal force on the bead is equal to M into, R is L, theta dot is alpha t whole squared, therefore it is ML alpha squared t squared. So there is a frictional force between the bead and the rod, and we know what is the reaction force on the bead due to the rod. That the reaction force on the bead due to the rod, N, is there. Therefore the frictional force in the limiting case limiting frictional force, therefore the limiting frictional force is equal to mu times N, that is equal to mu times N is M alpha L. Okay, so for condition for slipping is, for slipping is equal to, this frictional force must be equal to the centripetal force. This frictional force must be equal to the centripetal force. So from this we get this at this particular time t is, so M and M will get cancelled, L and L will get cancelled, one alpha will get cancelled, I will have mu by alpha, I need to take a square root of that. So what are the concepts which are tested in this particular problem? First thing is, you should realize that since alpha is constant, omega is not constant. Many students know by what I can say default, they will put an arrow around this rod rotating and put an omega, take omega to be constant, which is wrong, right? Then second thing is, as the bead moves along the rod, okay, there is a reaction force on the bead due to the rod, that is there. Then there is also a centripetal force on this bead, right? So for slipping, what will happen? The frictional, limiting frictional force must be equal to the centripetal force. Only then, till then it will survive. So this happens at this survive in the sense that this mass will remain on this rod. After that it will slip off. Okay. Now we will do another problem which involves, there is one more concept which is called toppling, slipping and toppling. We will explain what it is. So what I have is, I have a cubical block. I have a cubical block. There is a force acting on this cubical block here, F. So length of this cubical block is L, edge rather. So this is a horizontal surface, but there is it's a rough surface. It's a cubical block. Resting on a rough horizontal surface. The coefficient of friction is such that the coefficient of friction is so high such that the block does not slide before toppling. The coefficient of friction, it is given. The coefficient of friction is so high is such that the block does not slide before toppling. So as the horizontal force is applied, there is a tendency for this block to move along, translate. On the other hand, the coefficient of friction is so high, then what will happen? The block would only topple. So we need to calculate the minimum force, calculate let the F minimum for the block to topple rather. Okay, it's a fairly simple problem, but we need to realize. Now let us mark the various forces acting on it. We'll again redraw the diagram. Block, force, right? And now this is the center of mass, mg. So initially the normal reaction, when you are not applying any force, the F is not there, then the normal reaction would be at the center of mass of the cube such that it opposes mg. However, since the horizontal force is there, gradually the normal reaction would move and it will exactly topple when the normal reaction coincides with the side of the cube. Now, since it has a tendency to topple like this, the frictional force has to act down in this direction, opposing the motion. Right. Okay. Now sigma F, what are we going to do? The sum of all the forces along y direction is equal to, there is normal reaction acting upwards and then mg acting downwards. So is equal to, so we write all the this gives these two balance, or n minus mg 0 I should write. I am writing like this. Similarly, when I consider the forces, all the forces acting along x direction, now the horizontal force is capital F. This must be balanced by frictional force. That's it. Now we will take torques. We will write the torque equation about the C. We will write the torque equation. The torque equation about the center of mass, center of the cube. right? So F into L by 2, this distance is L by 2, then plus F into L by 2 F into L by 2 is equal to the normal reaction N into L by 2. So this distance is also L by 2. So this gives capital F plus frictional force is equal to N. And we have got it earlier, capital F is equal to 2F, therefore 2F is equal to N. And what is N? Normal reaction is F plus S is N, therefore this implies F is equal to N by 2, and we have showed that N is mg. We already have it when we balance the forces along the y direction. What is interesting about this problem is you need not know what is the value of mu, because the question is what is the minimal force that is required to topple it, right? And what are the things we have made use of? It is essentially force balance equation along x direction and force balance equation along y direction, and taking, and there are essentially speaking there are three forces. One is capital F, the horizontal force, and little f, which is the frictional force, and N, which is the normal reaction. So take the torques and equate them and you will get, and the problem is solved. F minimum. In fact, it is amazing that minimum force that is required is half of the weight of the body. Now we will move on to a problem. Sometimes people would ask questions involving rotational motion and clubbing it with something else. It all depends on the ingenuity of the examiner. There is one problem involving atomic physics, diatomic molecule, any diatomic molecule, rotational frequency, diatomic molecule, rotational frequency, and quantum theory. Sometimes such problems which club concepts from different branches of physics, they would strike terror. However, one needs to look at them rather carefully with some patience. Right. Now, what does a diatomic molecule do? A diatomic molecule, you have two atoms. So they can rotate about an axis with a frequency omega. So this distance is x. So what is this? This is the this is separation of atoms. X is the atomic separation between the atoms. Okay. Now we are going to treat atoms as point particles, but they have masses. And now we will take the case of oxygen atom. oxygen atom. For the oxygen molecule, you know, two oxygen atoms can combine to give you oxygen molecule. The separation between the atoms is 1.20 into 10 to the power of minus 10 meters. All this data will be provided to you. And mass of the atom, mass of the oxygen atom rather, mass of oxygen atom is equal to 2 points. This data is also given 2.66 into 10 to the power of minus 26 kilograms. Now, what is that you are asked to calculate? You are asked to calculate what is the frequency of the calculate the rotational frequency. Calculate the rotational frequency. Okay. Now, how are you going to do about it? First thing I realized that these two atoms, this molecule has a moment of inertia about the center. So, moment of inertia is equal to the standard MIRA squared. This is equal to m into x by 2 whole squared plus m into x by 2 whole squared. Right? So just leave it as it is, mx squared by 2. Now according to quantum theory, the fundamental unit of angular momentum, right? The fundamental unit of angular momentum according to quantum theory. Is h cross. What is the value of h cross? This data will also be given to you. 1.054 into 10 to the power of minus 34 kilogram meter squared per second. Okay. Therefore, from the given data, I can calculate what is the moment of inertia of the object. Therefore, moment of inertia into the omega, namely the rotational frequency, this must be of the order of h cross. Therefore, omega is equal to h cross divided by I is equal to 1.054 into 10 to the power of minus 34 kilogram per meter squared, kilogram meter squared per second. This divided by moment of inertia is, I have calculated this in the mx squared by 2. M is 2.66 into 10 to the power of minus 26 kilogram, that by 2 into x square. X square is this atomic separation, square of the atomic separation, that is 1.20 into 10 to the power of minus 10 meters second squared. And you can do this simplification and then you will get to be, it should be of the form, its value is about 5.2 into 10 to the power of 11 radian per second. In fact, it is amazing that this value more or less agrees with the experimental one. It really proves that this molecule actually has a rotational frequency. Most of these molecules, they have rotational frequencies. Okay. Time ka sir? All time for 5 minutes sir. I will see something which I can do, a simple problem. 50 ஆயிடுக்குல இப்போ 50 ஆயிருக்கு, பட் கொஞ்சம் டைம் வேஸ்ட் ஆயிருக்கு நமக்கு இல்லையா? ஓகே. We'll do a problem involving angular momentum, torque, etc. Let me state the problem. A rigid rod of mass capital M and length L rotates in a vertical plane about a frictionless pivot. This is the origin. Frictionless pivot through the center. A rigid rod of mass M and length L rotates in a vertical plane about a frictionless pivot. Through the center. Okay. Now this is so this frequency is given, let us say. So once the omega is known, linear velocities of m and m2 can be calculated. What are the various quantities which can be calculated? First, there is the moment of inertia of the system. First, mi of the system. Mi of the system. Mi of the system. So, mi of the system is equal to the moment of inertia of the rod about the center is ml squared by 12 plus little m1 is the one of the masses, that into about the center L by 2 whole squared plus m2 into L by 2 the whole square. This is equal to, this value would be L squared by 4 into m squared by 3 into m by 3 plus little m1 plus little m2. Sir, number 60 minutes editing time waste. Okay. Now, the system can rotate with a constant angular velocity omega. That is one data. So once omega is known, omega can be related to the angular momentum. So the angular momentum of the system is, once omega is known, L can be calculated. Therefore, what we have, L is equal to I omega, right? So this is equal to, we already calculated the I, L squared by 4 into m by 3 plus little m1 plus little m2, that times omega. Now there is a torque on the system, right? Because there is one m1g, there is another m2g forces. Therefore, torque on the system is equal to 3. The torque on the system first, tau 1 is equal to m1g into this angle, suppose I call it as theta. Therefore, this is L by 2 cos theta. Okay, m1g into L by 2 cos theta. So if I L by 2 cos theta, this distance, similarly this distance. So what about this? This is out of the paper. The torque, no, it has got a direction. So this is out of the paper, out of the plane. What it means is out of the plane. Tau 2 is equal to, similarly, m2g into L by 2 cos theta. But this is into the plane. Therefore, total torque is equal to half of m1 minus m2 into L cos theta. So this will act out of the plane if m1 is greater than m2. So this is if m1 greater than m2 into the plane if m2 less than m2. Since I alpha is equal to L, we can calculate alpha, namely the angular acceleration. So alpha is equal to tau total by I. So this you will get 2 times m1 minus m2 into g cos theta divided by m by 3 plus m1 plus m2.